Good morning. Okay, time for today's lecture. Okay, now the topic of today is still frequency domain analysis. However, today we will switch our attention from signals to systems. Okay, now let's review what is signal spectrum. What does it tell us? Signal spectrum is pretty much the frequency content of the signal. That is, by visualizing a picture like this, we can understand the frequency composition of that signal, all right? So then naturally, the next question is, what is spectrum? And it has everything to do with frequency response. Remember that we saw this spring mass damper system before. Under the condition of force acceleration, which means there is an external force, RT, applied to this mass, all right? And in this particular case, when our attention is on the frequency response of this spring mass damper system, then the input force is this sinusoidal signal, which has an amplitude of f0 and a variable frequency omega, which means omega is a parameter whose value can be changed, for example, from 0 all the way up to infinity, okay? So frequency response of this spring mass damper system is to help us understand such a system, how will it behave under such an excitation? And more importantly, how the response pattern of our spring mass damper system changes with this frequency of omega, all right? Now, we also these mathematical derivations before. Here, we assume based on the technique we learned in the course of engineering mathematics, we assume particular solution like this, okay? Where does this formula come from? It comes from the method of undetermined coefficients. The method of undetermined coefficients tell us if you have an input like this, if you have a forcing function like this, you can assume the particular solution to be a linear combination of cosine and sine with the same frequency. And that is exactly what we are doing. Now, the next thing we need to do, remember, we are seeking for the solution. Therefore, we need to determine the value of A and B. To do that, we simply take the first and second derivative of this particular solution and substitute them into the differential equation and equate the left-hand side and right-hand side of the equations, and from which we can determine the value of A and B, all right, which are summarized in these two equalities. Next, instead of using such a representation, which involve both cosine and sine, we prefer to rearrange the representation into this format, all right? Where C star is this, and eta is this. I will not go through the mathematical details here because we have done that before. Now, the techniques of how to go, the mathematical technique of how we go from here to here are all given in this page, all right? Are all given in this page. Now, in this page, hopefully, we will also briefly review the connections between trigonometry Fourier series and compact Fourier series. Remember that we told you that CM represents the spectrum, amplitude spectrum of FT. Similarly, theta n is the phase spectrum of FT. Together, they represent the frequency content of FT, all right? And we can plot them, okay, as a frequency of omega. And this is what we call amplitude spectrum of this spring mass damper system. And this is its corresponding space spectrum, okay? What do you see here? The first thing we can learn from this family of curves is that the amplitude spectrum, that is the value of C, is actually a function of omega, all right? That, what does that tell us? It tells us even with the same amplitude, if this forcing function has different frequency, then the response of this spring mass damper system will not be the same, okay? For example, if for example, what happened is in the low frequency bands, C star divided by F0 is approximately 1, all right? But as frequency increases, if you look at the case of C equals to 2, it will decrease monotonically with frequency, all right? However, if C is equal to 1/4, okay, it will increases in the first phase and then decreases as the frequency becoming higher and higher, all right? So, nevertheless, okay, this represents the amplitude spectrum or the frequency response of the system. Generally speaking, this is the amplitude spectrum. This is the phase response. But generally speaking, when we talk about frequency response, more often than not, we refer to amplitude spectrum, all right? Now, the next thing we want to do is to study system spectrum, that is the frequency response of the system in a more systematical fashion, all right? Now, remember that how do we represent a system? In a time domain, we represent a system by a differential equation, right? In the X domain, by taking the Laplace transform of that differential equation, we come out with a transfer function, right? And that transfer function, let me put it this way, okay? this is what we have. Let's say this block represents the system, and ft is the input, yt is the resulting output. All right. Now, assume the input is delta t, which is an impulse function, and the result is denoted as h of t, which is what we call impulse response. And we all know that the zero-state response is actually the convolution integral of the input and the impulse response. Okay, so in this regard, it is clear to us that h of t as a signal actually characterize every aspect of the system. All right, it represents everything of the system. Okay, every detail, every piece of information, every property of the system. All right, so that is the reason why by only using h of t to represent the system, we can predict, or we can calculate, or we can estimate what is not really predict, estimate. We can actually come out with the real output. Okay, and we all know that in the x domain, after taking the transfer function of the differential equations, we have this, okay, which means if I multiply the transfer function with the input, I will have the output. Okay, so remember that I told you this is amazing result, an amazing formula, okay, a wonderful equality, because by using this simple equation, you can easily relate the interaction between input and output. What do I mean by easily relating two of them? It means all I need to do is using a simple mathematical operation, which is multiplication. Then I can determine what the output is when the input and the transfer function are given. Okay? Now, by taking the inverse Laplace transform of h of x and of f of x, I have this. Okay? So if I have a multiplication in the x domain, what I have in the time domain is convolution, and vice versa. Okay? Now, these results are given in the x domain. And x domain is originated from the Laplace transform. Now, here in performing frequency domain analysis, we don't use Laplace transform. The basis for spectral analysis, at least the mathematical foundation for frequency domain analysis, is Fourier transform. And if you recall, okay, we told you that if the input is a capture signal, all right, and if I replace x by j omega, I can actually convert Laplace transform directly into Fourier transform. So if this is the truth, by replacing x with j omega, and by assuming I have a capture input, I actually have this equality. That is y of omega. The Laplace transform of the output is actually the product of the Fourier transform of the output is actually the product of the transfer function in the frequency domain and the Fourier transform of the input signal. Okay, now, so here, the transfer function is very important, all right? Now, I apologize here, in this page, transfer function is denoted by h, but in this particular slide, we assume g to be the transfer function. Now, as a transfer function in the frequency domain, it is actually a complex number. Why is that the case? Let's look at a simple example. This is an first order system with a zero initial condition, y of 0 equal to 0. I'm sorry for the Chinese character, but its state response is this. Okay, we showed this result before. So if you don't understand where does it come from, I strongly suggest you go back to our previous teaching materials, okay, or previous videos, okay. All right, now let's take the Laplace transform of this differential equation, and this is what we will get. The capital Y is simply the Laplace transform of Y, and capital R is simply the Laplace transform of R. So by taking Laplace transform of the differential equation, again, we have an algebra equation. Now, by definition, transfer function is the ratio of the Laplace transform, the ratio of the Laplace transform of the output to the Laplace transform of the input. This is the definition of transfer function. And from this equality, G for this, the transfer function for this simple first order differential equation is this, all right? I'm pretty sure these, at least I strongly hope these two views are redundant. I don't have to review these materials for you. You already know them by heart. Okay, I truly hope so. Okay, I truly hope so. But just in case this is not that's not the case. Okay, let's go over this again. Okay, so in this particular case, for this fourth order system, this is our transfer function. Now, the next step is that we want to go to the frequency domain. So I replace x by j omega. All right, and this is what I have. Now, what I have is g of j omega, which is here, now become this. Okay, this is my transfer function. Since I'm interested in amplitude spectrum, therefore, I need to know the magnitude of this transfer function. All right, and the magnitude of this mathematical representation is actually this. Okay, we all know that the magnitude of a complex number is the square root of the sum of the real power, the square of the real power, and the square of the imaginary power. Okay. Similarly, we can determine the phase response of this, or the angle of this transfer function, okay, and which is this, all right? Now, this is only one example. What I want to do next is to generalize such a result, okay? So we can take care of all the transfer functions for different types of linear time invariance, linear time invariant continuous system. Now, here in the beginning, I assume g of j omega can be represented like this. That is, since it is a complex function of frequency. So, as a complex number, it always have a real power, it always have an imaginary power. So let's switch our attention to the 2D complex plane, where the horizontal axis corresponds to the real number and the vertical axis related to the imaginary number. All right? And to do that, what we are performing is actually we want to do all the mathematical derivations in the Cartesian coordinate system. And we don't want that, okay? Because because it's not the easiest way for us to do future mathematical manipulations. What we want to do is we want to set out a polar coordinate representation for our transfer function. So again, we set up this right angle, all right? Now, well, apparently, since R is the real part of our transfer function, so this is R. Now, since X is the imaginary part of the transfer function, so this is X. Remember, the horizontal axis is correlated. It represents the real part. The vertical axis represents the imaginary part. So this is R, this is X. So the distance, I'm sorry, the size, okay, the length of this line is apparently this, which is this, okay? If I divide these two things by this is what we have. From these triangles, we know that this is actually cosine theta, right? And this is actually sine theta. And from the Euler formula, we know that e to j theta is actually cosine theta, j sine theta, all right? So the next step is, let me rewrite this as this. Will this represent the amplitude spectrum of the transfer function? And this, which is now written as the angle of G, represents the phase spectrum of the system. Now, to make this representation even simpler, next time when we represent the transfer function, I can simply represent it as this, okay? Where this magnitude represents the amplitude spectrum, and this so-called angle of G is the phase spectrum, all right? Now, so by definition, okay, this magnitude comes from here, okay? That is square is actually the sum of the square of the real part and the square of the imaginary part, okay? And this, of course, comes from these triangles, okay? All right, so next time when you see I represent a transfer function like this, okay, don't be confused, okay? Because if you forgot what we are doing here, okay, when I write a transfer function in this format, it can be very confusing. It can be, you probably don't know where do they come from, okay? You probably will see such a representation very unnatural. And that would be a pity, because how do we have such a representation? The reasons are all given here. And this process is not complex at all, okay? Now, let's review a simple math technique. Now, what we are dealing with is 1 over A plus JB, okay? That is, I have a complex number, but the complex number actually appear in the denominator, all right? So what I want to do is, let's assume this is a transfer function, all right? Now, Okay, and I want to know its magnitude. For its magnitude, it's actually easy. Okay, this is magnitude because we all know that the size, the magnitude as a complex number is always the square, the sum of the square of the real part plus the sum plus the square of the imaginary part, and then we need to take a square root. Now, the trick here is what is the angle of this complex number? To do that, the first thing we need to do is let's multiply the denominator as well as the numerator by a plus minus jb, which is the complex conjugate of the denominator. And we all know that when you multiply a plus b with a minus b, what you will get is a squared minus b squared. And let's do that, okay? Use that formula here, and this is what I will get, all right? And in this case, when we look at an angle, okay, the angle is actually determined by the numerator because the denominator is nothing but a number. It only has a real number. So it has nothing to do with the angle. And this angle, what is this angle? Let's look at this figure, okay? For a plus jb, for that particular number, its location is at this particular point. However, for a minus jb, this point or this number, this number is actually located here. If you compare the angle of a plus jb with a minus jb, if its angle is theta, then its angle is minus theta. All right? Okay. So whenever you see a representation like this, that is, you have a complex number where you have such a representation where the numerator is a real number and the denominator is a complex number. To determine its magnitude is a piece of cake. To determine its angle is also not difficult. All you need to do is, you know what it is, and then you put a minus sign in front of it. Why? Because of this result, all right? And this is exactly what we do here in taking care, in deriving the amplitude, the phase spectrum of this first order system. This is why we have a minus sign here, all right? Because the complex number appears in the denominator. All right. Okay. Now, one of the most important results we just saw you is this equality. And I also told you that for any transfer function or any result of the Fourier transform, I can actually represent it as this or this, all right? Now, let's combine this result with this equality, okay? And see what happened, okay? Again, this is the Fourier transform of the output. This is the Fourier transform of the input. This is the spectrum of the system. That is, this is the transfer function of the system in the frequency domain, all right? Now, with a polar when I represent y omega using its polar coordinates, this is what I have. I can do the same thing to f and h. Now, since e to when I multiply ejx with e to j y, what I will get is e to j x plus y. All right? So the product of f of omega and h omega is actually this. For the, I should put it this way. When I times AEIX with BIJ, okay, JY, what I will have is A times me times A times E to the power 2J of X plus Y, all right? Now, this is an equality that we want to use here. And this is, of course, this equality, of course, is always true, okay, because it has been mathematically proven. Now, A is in this case is this, the magnitude of F. B in this case is this, the magnitude of the transfer function. And X and Y, of course, are the angle of F and the angle of the transfer function. So by using this equality directly to the right-hand side of this equality, this is what I will get, all right? If this is the case, we know that, this has to be equal to this, all right? If they are equal, that means, remember, these are polar coordinate representations. When they are equal, their polar coordinates have to be equal. Each of their polar coordinates has to be equal, okay? So when it comes to the magnitude, they have to be equal. When it comes to the angle, they have to be the same, right? So these are two very important results, because these two equations tell us what Session spectrum really means to us, okay? Remember, this is the amplitude spectrum of the, this is the spectrum of the amplitude spectrum of the input signal. This is the output, okay? When it comes to the amplitude spectrum, input and output, they have different amplitude spectra, okay, of course. But how do I go from input, the amplitude spectrum of the input, to the amplitude spectrum of the output? Okay, what is the role of the system? The role of the system is this. The system can revise the amplitude spectrum of the input by multiplying the amplitude spectrum of its own transfer function. Okay? Remember, these three things are non-numbers. Function of omega, function of omega, function of omega. Okay? So when you see this equality, you actually see infinite numbers of equalities, which means when omega is 0.1, you have one equality. When omega is 0.2, you have another equality. How many possible values do I have for omega? Infinite numbers of values of omega. So what I have is infinite numbers of equalities. Why is that the case? Because these three terms are all functions of omega. For any given value of omega, you have one distinct equality. Okay? Now, so the role of the transfer function when it comes to the amplitude spectrum has everything to do with this equality, which means multiplication is the basic operations. You multiply the amplitude spectrum with the amplitude spectrum of the input and of the system, and you will get the amplitude spectrum of the output. All right. Now, when it comes to the phase spectrum, similar thing happen, but similar, not identical. Here, what we have is multiplication, but for amplitude spectrum is addition, which is a simpler mathematical operation compared to addition, right? Okay. So please remember the learn by heart. Okay. Now, let me summarize the importance, the significance of these two important results. Okay. Now, here I assume what we have is a sinusoidal input for a stable LTIC system. LTIC means linear time invariant continuous system. If the input is a sinusoid, okay, A times cosine of omega 0 t plus phi, the steady state output is guaranteed to be a sinusoid at the same frequency, but with modified amplitude and phase. The first thing we can be sure is that the output, the steady state output, is also a sinusoidal signal. And more importantly, it's not just any sinusoidal signal. It's a sinusoidal signal that has the same frequency as the input signal. And its output will look something like this. All right? Now, based on these two equalities, its amplitude, which was originally A, now has 2 times the amplitude spectrum of the transfer function with omega equal to omega zeros. All right? And same thing happened to the phase. But here, what we have is multiplication. Here, what we have is addition. All right, Cap? There are separate things I need to clarify. The first thing is, what do I mean by steady state output? Because when talking about transfer function, remember that total response consists of 2 parts: zero state response and zero input response. Okay, zero response is associated with the impact of the initial conditions, and zero input response. Their input response is associated with the impact of initial condition. It has nothing to do with the input. By contrast, their state response explain the result of the input, not the result of the initial conditions. Okay, and transfer function is related to the zero state response, not the zero input response, right? That is why we have this result, okay? The transfer function times the input, okay? It does not multiply the initial conditions, all right? So here we talk about transfer function. And so the response is supposed to be related to the zero state response. But here the statement says what we are discussing is the steady state output. Why is that the case? It can be explained by the following sentence. For asymptotically stable linear time invariant causal system, the zero input response decay to zeros, all right, when time approach infinity, because it is asymptotically stable. So all the terms, when without any external inputs, all the response will decay to zero when time approaches infinity. So the steady state response is entirely the zero state response, okay? So when it comes to zero state response, okay, is all come from the transfer function, all right? Now, the second thing is, how do I know this is true, okay? How do I know the output, their state response, the steady state response is a cosine signal with the same frequency as the input sinusoidal signal? To answer that question, let's again use this equality. Now, what I have, let's assume this is our input, which apparently is a sinusoidal signal whose frequency is omega 0. What is amplitude spectrum? Of course, this is its amplitude spectrum. Being a sinusoidal signal, it only has one frequency component, which occurs at omega equal to omega 0. The reason why we have the minus frequency component does not mean minus frequency component exists. It does not exist. Why? Because minus frequency has no definition. But why do I have this? The reason why is we use exponential progressive representation. We introduce the concept of complex variable. And at the same time, the signals are all real numbers, okay? Okay, are functions of real numbers. So this negative frequency is just a mathematical byproduct, okay? It's not, there isn't any real physical entity correlate to this component, all right? And that is the reason why we talk about this many times. That is, amplitude spectrum is always an even function of frequency. And if you check out a Laplace transform table, if you take, Fourier transform table, if you take the Fourier transform of this sinusoidal signal, what you will get is this, all right? Which is, of course, this. If I multiply this with a spectrum of a system, let's say this is the amplitude spectrum of system. If I multiply, if I multiply this with this, what will I get? What I will get is a pair of symmetric arrows located at omega 0 and minus omega 0, okay? And this is the result, which come from here, all right? So if I take the inverse and then if I take the inverse Fourier transform, this is what I will get, all right? So we are pretty comfortable with, hopefully, with this result, which tells us that, let's say we have a system whose transfer function is g. If the input is cosine omega 0 t, then the steady state response or the zero state response of the system will be this, okay? Same frequency, okay? But different amplitude. Here, the amplitude is 1. Here, the amplitude is A omega, where A omega is the amplitude spectrum of the system. And here, the output compared to the input has an additional phase angle. And the phase angle happens to be the phase spectrum of the system, okay? All right. So what we learned here is that the transfer function H omega directly gives the steady state output for any sinusoidal input. This is the physical interpretation of the frequency response, okay? So this is the physical interpretation of the frequency response, all right? It all comes down to these two equations, all right? Okay, let's go one step further, okay? Frequency domain analysis. What does it really do? Two things. First is amplitude scaling. The magnitude, that is the amplitude spectrum of the transfer function, scales the amplitude of each frequency components in the input. If its value is larger than 1, that means that the system will amplify that frequency components, all right? However, by contrast, if the amplitude spectrum, the value of the amplitude spectrum of the transfer function is smaller than 1, then the system attenuates components at the frequency of omega s zeros. So in this sense, the system actually revises the amplitude spectrum of the input, okay? It can make it stronger or it can make it weaker. It all depends on the amplitude spectrum of the system, all right? And in addition to amplitude scaling, the second thing a transfer function can do in the frequency domain is frequency phase shifting, okay? The phase, the angle of the transfer function, shift the phase of each frequency component in the input, all right? So what we learned here is that we can predict the output for any given input by understanding how the system modifies the amplitude and phase of its constituent sine waves. Remember that every periodical signal can be represented as by its Fourier series representation, okay? And every component, each of the input components can be revised based on this result, okay? This result is good for any omega. It's good for omega 0, it's good for 2 omega 0, it's good for 3 omega 0. Any integer multiple of the fundamental frequency, all right? Now, let's look at the real examples. One good thing about the amplitude spectrum is it can be experimentally determined. For example, what we have here is a loudspeaker. We all saw loudspeaker before. It can be very, very cheap. It can also be very, very expensive. When I say expensive, it can cost you more than I don't know, more than 100,000 NT, all right? Even more, all right? So how do you determine the frequency response, the amplitude spectrum of a speaker? A loudspeaker is a device being, here, what we have in this picture is a speaker is a device being tested, and the frequency response plot show how loud it outputs different frequency, which means I will input sinusoidal signal with different frequencies into the loudspeaker, and I will use this microphone to pick up the signal this loudspeaker produce, and the sound pressure, the volume produced of these loudspeakers varies with the amplitude, varies with the frequency of the sinusoidal testing signal. And then I can plot the frequency response of, for example, this particular loudspeakers. All right, okay. And this frequency, you can see this frequency plot for loudspeakers as well as earphones, okay, provided that the manufacturer provide you such information, okay. But any good loudspeaker or good earphone manufacturers, they perform such a test to determine the frequency response of their loudspeakers or earphones. And sometimes they adjust, they modify their design for better frequency response, or at least frequency response they prefer. Okay. Now you can see that for this both sharp loudspeakers, it actually is unable to faithfully produce the bass. Okay, that is the low frequency components of the input signal. Why? Because it is simply not large enough. Physically is incapable of produce very deep bass. All right. Okay. So let me draw a conclusion here for the session spectrum. A session spectrum tell us how the system modify the input signal spectrum. All right, let's take a 10 minutes break. 那个，哎，把那个的，有两位同学哦，那名字给我一下。